Okay, good evening, everyone. Welcome to O-Level Physics lesson. My name is Mr. Chu, and today we're going to start the topic on current of electricity. Okay, as usual, before I go into the new topic, I would like to show you all the topic that you need to know for O-Level Physics. Okay, so we've done measurement, Newtonian mechanics, thermal physics, wave, and then now we are focusing on the purple part, the last part. We have gone through static electricity. That is when the current doesn't move. Okay, where the charges does not move. The charges are static. Okay, so from second topic all the way to the end, we'll be talking about charges that move. So when charges move, okay, there will be an electrical current. Okay, so this topic we're going to talk about current. Okay, then after that, after you know about current, then we can start forming simple circuits. Okay, then we'll talk about practical electricity and then so on. Okay, so this topic here, the second topic in this purple part, current or electricity, is the introduction to current. All right, are you all with me? Are you able to see what I'm saying? Okay, good. Okay, so let me go through the syllabus. Okay, so again, I have mentioned this overview before. Do you want to read again? Okay, don't need. Okay, so I mentioned about electricity and magnetism. They are actually part of the same thing. Okay, they are not separate. Okay, in primary school, you learn them as separately. In lower secondary, you learn electricity and magnetism separately. Okay, in O-level physics, you start to learn separately. But when we reach the last two topics, you realize that they are related. Okay, so the first topic we talk about is electric charges, they are not moving. Then we talk about charges that move. Okay, charges that move, and then we will not talk about current, voltage, and resistance. So this is what we are going to learn today. Okay, so let me show you what, wow, so many objectives. Okay, so for the whole topic of current or electricity, this is the objective. Okay, this is the objective. By end of this topic, you need to know all these objectives. Okay, first of all, you need to know that current, okay, that we learn in primary school up to now, okay, is all conventional. Okay, it is the opposite of electron flow. I'll talk about that later on. Okay, we need to know about EMF. Okay, so first subtopic, you need to learn about current. Second topic is second subtopic, we're learning about potential difference, the voltage. Okay, EMF and potential difference, they are the voltage. And then lastly, we will talk about the resistance. Okay, anybody up to here have any question for me? Okay, let me log into the Zoom first. Okay, y'all take another 1 minute break. Let me pause the recording. Okay, so for this topic, we are starting with the basics of electricity, okay, of moving charges. Okay, so the first part here, we're talking about current, which is the short form is I. Okay, the next two part is voltage. Okay, and then the last one is resistance. Okay, so you see down here, the three letters that I write down, okay, you may also want to jot down. They are the symbol for current, okay, voltage, and resistance. Okay, so in Sec 3, okay, in Sec 3, in primary school, okay, in primary school and in lower Sec, you just learn the thing called voltage. Okay, some of you in lower Sec, you will learn potential difference. Okay, now in O-level, why do we have two things? Okay, to me, they are both the same. For now, just remember that both are the same. They are both voltages. Okay, but do not use the word voltage in your explanation from now. Okay, these voltages can be broken up into two parts. So how to remember what's the difference between these two voltages? The first voltage is the voltage of the source. Sorry. Hey, how do you spell source? Can anybody help me? Suddenly I cannot spell source. Thank you. What's wrong with me today? S-O-U-R-C-E. Okay, so for electromotive force, the short form is EMF, or you can use V, okay, capital V. Okay, it is a measure of a source. A source can be a battery, it can be like your, what else? What other source do you know? Basically, the main source that we know is battery. Okay, so when we measure the voltage of a source, like a battery, we don't say voltage, we use the word EMF. Clear? Then potential difference is actually used for loads. Okay, whether you're measuring your buzzer, your heater, okay, whatever load that you actually is in your circuit, okay, we instead of using the word voltage, we use the word potential difference. Okay, so these are the basics before we start to create circuits. Okay, next thing let me talk about the symbol. Okay, symbol is for current is I. For voltage, okay, for these two, the symbol is capital V. And then for resistance, the symbol is capital R. Okay, there's no need for you to spell out all these words very long. Just remember I, V, and R. Okay, then for these three, they also have unit. Okay, what is the unit for current? The unit for current is ampere. Okay, the unit for these two is volt, V-O-L-T. And the unit for resistance, something new, it's not a letter in the alphabet, okay, is the ohm. Okay, so let me spell them to you. Ampere, volt, and ohm. Clear so far? Okay, so the one in green are the units for this quantity. And this quantity, we split them into current, V, and resistance. Okay, I like to say V, but when you write out, when you explain things in your exam, don't say voltage. Okay, either use EMF or PD, potential difference. And EMF is the measure of the voltage of an electrical source. Example, battery. Okay, whereas PD is a voltage of another electrical load. Okay, load, a load example. Okay, whether it can be resistor, it can be your speaker, okay, your bulb, okay, all these that you learned before, this PD is used to measure the loads. Okay, up to here, any question for me? If you are clear to this point, give me a yes reaction, everyone. If you are confused, if anything, give me a no reaction. Whoa, Oscar giving me hearts. Oscar, your mommy asking me feedback about you. So can you please be more responsive? Ryan and Beiguan, are you okay? Okay, so this is the subtopic of this topic. So let me go through quickly the learning outcomes. There are so many. Wow, hey, a lot. Okay, let me reduce the size a bit. Okay, these are all the learning outcomes. Okay, let me take a look first. Okay, the first three is talking about current. Okay, so all of you need to memorize. When you see the word state, okay, this candidate is you. You should be able to state that current is a rate of flow of charge, and that is measured in ampere. Okay, so how I want all you to remember, current, the symbol is I. Okay, when you see the word rate, do you all remember the word rate? I like to emphasize. Okay, let me give you a few examples. What is the definition of, can you state the definition of velocity? Okay, can all of you type it out? State what is velocity. All of you type out now. Okay, all of you need to actually state what is velocity. You all need to know. So can you all please type it out? If you are not sure, say help. Okay, say help if you are not sure. Okay, Yufan incorrect. Qiao Xing, well done. Beikuan, distance is not correct. Talking about velocity, not speed. Okay, so far only Chelsea got it correct. Yuting also correct, well done. Hao Rei is not distant, this is a vector, not a scalar. So you must change the distance to something else. Okay, so let me write down to you. So velocity is the rate of change of displacement. Do you all remember this? Okay, same thing. Acceleration is the rate of change of velocity. Clear so far? Okay, clear so far? I'll give another example. Power. Okay, in the topic of energy, work, and power, what is the definition of power? Can all of you state what is power? It's also the rates of, let's say, energy or work done. Correct? Okay, so the key thing I want all of you to understand from this example is the rate of. When you see the word rate of, it means divide by t. Okay, so V is actually equal to something divided by t. Acceleration is equal to something divided by t. Power is equal to something divided by t. Clear so far? Okay, clear so far? So if your formula have something divided by t, your definition will start with rate of something. Clear? Okay, so for velocity, it is the rate of change of displacement. So this displacement here, you put on top S. Okay, S stands for displacement. Velocity, you put on top, you put V. Then energy or work done, you put on top, you put E. Is that clear? Okay, now we go to this definition of current. Okay, current is the rate of flow of charge. Okay, so current is I. It's a rate of flow of charge. You see the word rate, you must write down the divide by T below. Understand so far? Okay, so what is the rate of flow of charge? So the flow of charge you learn in static electricity is the Q. Do you all remember that? Okay, so the formula for current, which all of you must remember, is current is, okay, let me show you my mouse. Current is the rate of flow of charges. Q is the charges. And then if I were to rearrange this formula, if I make Q is as a subject, I'll get Q equal to IT. And this Q equal to IT is what my secondary school teacher teach me. Just remember Q is it. This equal sign, just remember is IS. So Q is it. Okay, that's how I remember this formula from Sec 4 till now. Okay, if it's useful for you, you can also remember this way. If you have other ways of remembering, okay, go ahead to remember your other way. Understand so far? Okay, so you all understand the meaning of current is, okay, let me go through the meaning of charge. Q. Do you remember Q? Q is like is either positive charge or negative charge. And then 1 coulomb of charge. Okay, 1 coulomb of charge is about 6 times 10 to the power 23 charges. Do you remember that? Okay, so what does this mean? Current is not how much charge go through the wire. Okay, how much charge go through the wire is charge, which is Q. Okay, how much charges, how much of that positive or negative charges flow through is the charge Q. So what is current? Current is how many charge go through the wire every second. Is that clear? I repeat myself. If you talk in a very simple way, current is the amount of charges that go through that point every second. Can? So if you on your aircon for 10 hours, your current will still be the same number because the current is how much current moving through that wire every second. But the amount of charges that flow through in the 10 hours is definitely more than the amount of charges that flow through in 1 minute. Is that clear? You need me to repeat? Okay, if you on your handphone, if your phone has a ring, to charge your handphone, your wire can tell you this is a 3 ampere rated wire. What does that mean? It means that every second, 3 coulomb of charges can flow through that wire. Okay, so whether you charge your phone for 1 minute or 10 minutes, the current will still remain as 3 ampere. Means every second, 3 coulomb of charges will flow through the wire. However, 10 minutes, there'll be more charges going through because 10 minutes, there are how many seconds in 10 minutes? There are 600 seconds, right? So there are 600, you'll have 600 times of charges flowing through in 10 minutes compared to 1 second. Did I make this clear to you compared to before, or you already know? Okay, if you already know, type already. If it's something new that is refreshing to help you understand better, you type new. So I know whether am I explaining better for you. Okay, thank you, Yiting. She says new. So Chelsea already know, but most of you say new. Okay, so I hope the way I explain help you understand what this current is. Clear? Okay, next. Let me. So we talk about current, and the unit for current is ampere. Ampere is a guy, is a famous scientist. So okay, let me remind you again. If the unit is named after a famous guy, you will spell out the unit. It starts with a small letter. Okay, another famous guy that is named, another unit that is named after a famous guy is Newton. So when I say this is a 5 Newton force, so when you want to spell out, you spell out with a small letter. Is that clear? But when you write down in short form, it's normally capital letter. Same thing, the symbol for ampere is a capital letter A. Okay, later we'll talk about ohm, it's the same thing. Ohm also spelled in a small letter. Okay, so up to here. Okay, next thing we're going to talk about is conventional current and electron flow. So all the things that you have learned in the past, plus all the things that you're going to learn today and this year, is all conventional current. Okay, everything, all your calculation will be based on conventional current. So if you were to draw a circuit, you were to do some calculation, you'll be all based on conventional. And what does conventional means? Conventional means that we are assuming that the positive charge is moving. Okay, so that your calculation can make sense. And when they first discovered electricity, they thought that it's the positive charge that moves. Okay, so therefore, all the electricity started off talking about conventional current. Okay, so we are assuming that positive charge move. If a positive charge move, all your calculation is correct. Okay, so in all your calculation, we are based on conventional current. Okay, let me draw a very simple car circuit that you have learned before in primary school. Okay, so this is a circuit. This is the positive side of the battery and the negative side of the battery. So conventional current states that plus will go to minus, correct? Okay, plus will go to minus. So the direction will be like this. The direction of the current will be from plus to minus. So this red arrow is the conventional current. You learn this in primary school up to now, and then for O-level, you're going to do this as well. Okay, we are assuming that current move from plus to minus. Make sense? Okay, just like magnet. Magnet, the pole moves from positive to negative. Your electric field, same thing, is the positive charge moving in that direction. So everything you're going to learn is very simple. It's all from plus to minus. However, one day, one scientist, I cannot remember who, discovered that it is not the positive charges that move. Okay, you have learned in chemistry before. Okay, positive charge is the proton. It's stuck in the nucleus. Okay, the nucleus doesn't move around. Okay, so the positive charge in a metal does not move. Okay, on the other hand, it is the electron that move. Okay, electron that move. Okay, so for O-level, to make things not confusing, everything you talk about will be conventional current. The only thing you need to know, but you don't need to apply, but you need to know in your head is that, yes, you learn conventional current. Yes, you learn that current move from plus to minus, but go down to the electron level. It is not the positive charge that's moving, but the electron. Okay, so what happened here? In actual fact, all the electron will be moving in the opposite direction. Okay, the electron will be moving in the opposite direction. Electron, I can also write this way. So that is what actually happened. Okay, but in your drawing, in your calculation, in your explanation, we all use plus to minus. So this plus to minus, we call it conventional current flow. But in reality, that's not how things work. It is the electron that's moving in the opposite direction. Okay, so for part B, are all of you clear now? Okay, if you are clear, give me a thumbs up and then remove all your yes reaction. If you are clear, give me a thumbs up and then remove your yes reaction. Thank you. Howard, you okay? Thank you. Howard, remove your yes reaction. Okay, lastly, I talk about current is a rate of flow of charge. So from here, you can see the current is equal to the charge divided by T. So Q is it. Okay, so this definition is I equal to, sorry. So from this definition, you know that I is equal to Q over T. So if you make Q the subject, you will know that this formula is Q is it. But you don't like Q is it, you can also remember I equal to Q over T. Okay, so you're going to solve problem using this formula. Either Q is it or I equal to Q over T. If you want to learn your physics better, understanding better, you can memorize this formula. You want to make yourself life easier, you can memorize this formula. So either formula that you want to memorize is fine. All you need to know is how to rearrange, how to make Q the subject, how to make I the subject, then you'll be okay. Okay, so that's all for current. Any question for me? Okay, so we're going to talk about the V. The V is from here to here. Okay, so looking at this outcome, all of you should be able to define what is EMF. Okay, in primary school, we don't use EMF, we use V. So from O-level onwards, we use EMF. Okay, symbol, you can still use V, but don't use the word voltage anymore. Don't use the word voltage. Previously, you used the word voltage. So the voltage erased from your brain. Replace it with EMF or PD. PD is here. Clear? Okay, so the key difference between EMF and PD, let me highlight to you, which I already mentioned earlier. EMF is source. PD is a load. Okay, it is a load. So this is the load. Okay, source provide electricity, the energy. The load use up the energy. Is that clear? I repeat, the source supply the energy. The load use up the energy. Also for a source, for a supply, you use the word EMF. For load, you use the word PD. Okay, so let me draw that primary school diagram that all of you are very familiar with. Okay, so this is a very simple circuit diagram which you all learned in primary school. The red line is a wire. So this long and short line is the battery. Okay, this circle and across is the bulb. So this is a source. This battery provides the energy. So this battery is a source. Clear? Source. So how do we measure how powerful this source is? Okay, so this measurement we calculate is called the EMF. Okay, so we do the same thing. You want to see before and after the point. Okay, I repeat. Before and after the point, I got this point here that's after the point. I got a point here that's before the point. I want to measure the difference between these 2 points. So the source, this battery, actually increase the potential of the point. For example, I can tell you that this point is 0 volt. After I put a battery in a closed circuit, this point become 5 volt. So what does this mean? This means that the source here, the battery, increase the voltage by 5 volt. So instead of the word voltage, if I were to put a voltmeter in between, this voltmeter measure the difference between these 2 points. Okay, this voltmeter measure the difference between these 2 points, and then this battery increase the potential here from 0 to 5. So this battery has a voltage of 5 volts. Remember I told you don't use the word voltage. So change the word voltage to EMF. So this battery supply a EMF of 5 volts. Clear? Okay, same thing. The bulb, okay, use up your electricity. So before and after, there are 2 points. Okay, so to measure how much energy is used up by the battery, by the bulb. Okay, although what I say energy, that's not correct. But just assume that it's something like energy. So how much of the electricity is used up by the bulb? Okay, we measure the difference between these 2 points. Okay, so for example, the battery increase the potential from 0 to 5. And then from this point all the way to this point, there's nothing here. There's no component. There's no battery. There's no bulb. There's no load. There's nothing at all. So this point will also be 5 volt. Correct? So same thing. On the right side, there is no point. There's nothing. Sorry, there's no load. There is no source. There's no component. So if this point is 0, and here is all connected by wire and nothing in between, this point will also be 0 volt. Understand so far? So if I were to put a voltmeter between these 2 points, this voltmeter will measure the difference between these 2 points, and then it will give you a result of 5 volt. Okay, so I can conclude that this bulb has a voltage of 5 volt. As I mentioned earlier, in Sec 3 and Sec 4, O level, don't use the word voltage. You say the potential difference. Okay, the potential difference of this bulb is 5 volt. Okay, the EMF of this battery is also 5 volt. So the battery raise the potential to 5, and then the bulb drop the potential to 0. Understand so far? Okay, so this is the idea. So now I'm going to give you all the definition. Okay, I'm going to give you all the definition. EMF is the work done by the battery in driving 1 unit of charge around the whole circuit. So for example, if I have an EMF of 1 volt, okay, if an EMF of 1 volt, what does it mean? It means that the battery can provide 1 joule of work or 1 joule of energy, okay, by 1 coulomb of charge around the circuit. I know it sounds, sorry, 1 coulomb, not 1 Q. Okay, this is something that is not easy to remember, to understand, and to conceptualize. After O level, then I realized. So during my 2 years in secondary 3 and 4, I never remember this definition. But that doesn't mean you also don't remember. You must remember, okay? Okay, so what does this mean? This means that voltage, okay, I use the word voltage because you are familiar with the word voltage. Voltage is the amount of work done by the battery to drive 1 unit of charge around the circuit. Remember last time I told you 1 unit of charge is about what? 6 times 10 to the power 23 charges, right? So if I have this amount of charge in the whole circuit, if I put a 1 volt battery there, it means that the battery provides 1 joule of energy to push 1 coulomb of charge in around this circuit. Is that clear? Okay, so from here, are you convinced that the formula is V is the amount of work done? Okay, work done, I use capital W, or you can use energy lah, or E, same. Okay, that is done by the source for every 1 unit charge around the circuit. So this is the general formula for both EMF and PD. So let me go to point number G. So can you see the potential difference across the bulb is the work done, is the amount of work, okay, amount of energy used to drive 1 unit of charge through this component. Is that clear? So the EMF is the amount of work by the battery to drive the same 1 unit of charge. It's like how much energy supplied by the battery. Okay, whereas the bulb, okay, the PD is like how much energy is used for every 1 coulomb of charge moving across it. Okay, I know this is not easy to explain, but this is the definition. So now my question to you is, after I try to explain the definition of EMF as well as PD, do you understand it better or worse or no change? Can you give me, can you write down in the chat? Do you understand better now, or do you understand it worse, or there's no difference from what you already know? Okay, can you type it down in the chat to let me know? Wow, Chelsea, your teacher teach you very good. Huh? Most of the people say better. How about the rest of you? I've asked a question. Why there's no response? Yeah, another reason why I did not learn this in my secondary school is because in my syllabus last time, right? This is not required for us. It's only started maybe about 15 years ago. Before that, this formula is not required during my time. Yeah, that's why when I see this formula for the first time, I was confused. Okay, so the easy thing for you all to understand, not remember, to understand is that EMF is like how much energy it produces, but it's not the energy. Okay, it's not the energy, but to understand better, just remember it's like how much electricity it actually supply, whereas PD is how much electricity does it use up. Okay, but it's not in terms of energy, it is in terms of energy required per unit charge. That is the official and the correct definition of EMF and PD. But for understanding purpose, just remember, okay, EMF is how much electricity it provide, and then PD is the amount of electricity it takes up. Clear? And to me, EMF and PD are the same, just that one is the source, the other one is the load. And the term PD is very clear. It is the potential difference. Okay, at each point there's a potential. Okay, the point here is 5, the point here is 0. So the difference between these two potential is the PD. Okay, so the word PD makes sense to me. Okay, because if you grow up, you become an electrician, you have a voltmeter, you just point the two ends of the voltmeter to the 2 points, it will tell you the difference between the 2 points. The difference is the PD. Okay, and it's not wrong to say that EMF is also the PD between these 2 points, because that's the difference between these 2 points. Okay, but the official definition is called EMF. It's an EMF. So some students get confused because there's a word force inside EMF, but this is not a force. Neither is it energy. Okay, it's the work done to drive one unit charge. Okay, that is the definition of EMF. Clear? So for understanding purpose is how much electricity is supplied. Okay, for this one, for the bulb is how much electricity it uses up. That's all. That's for your understanding for now. Okay, but the definition is EMF is the amount of energy, okay, to drive one unit of charge around the circuit. And then for PD is the amount of energy required to push one unit of charge across this component. Is that clear? Okay, so I've explained D, explained G, okay? And let's look at E. Calculate the total EMF when several sources are arranged in series. So for EMF, we just add them together. Okay, this one we'll talk about that when we do question. Then for F, you need to know that both EMF and PD, the units is volts. Can you see here? Volt is another famous scientist. Okay, and he after he passed away, they named the unit for EMF to him. Okay, likewise, his name supposed to start with capital V, but in unit you spell as a small v, but the symbol you use capital V. Okay, like your battery is 1.5 volt. Then, so your normal AA battery, okay, a normal AA battery is 1.5 volt. What does it mean? If your circuit have a lot of things, okay, but the amount of charge, let's say in one round, it uses up 1 coulomb of charge. Sorry, 1 coulomb of charge. Okay, so 1.5 volt means it actually supply 1.5 joule of energy just to push 1 coulomb of charge in the whole circuit. Is that clear? Okay, I know it's not very clear because I'm also not convinced what I'm talking myself, but that's the definition. Okay, any question for me? No question, no way say anything means no question. Okay, so let's revise, just to revise. We have talked about 2 formula. The first formula is Q is it. The second formula is V equal to work done. Okay, I use energy. Energy divided by charge. Okay. Okay, so we have learned these two formulas so far. Now we talk about resistance. The rest of this thing here is resistance. Okay, so as I mentioned, resistance, the symbol, you don't like to spell, just type capital R. Okay, so this is the symbol of resistance. Okay, so resistance, what's the formula? Down here. Okay, so this is what you will learn, you need to learn. From this definition, you know that resistance is equal to V divided by I. Okay, V divided by I. How many of you like this formula? You learn this in lower side as well. If you like this formula, type like. If you don't like this formula, type hate. Oh, Oscar like this formula. So all of you remember it as R equal to V over I, is it? So only Oscar and okay. Bei Kwan says he remembers it as R equal V over I. Okay, so you can see over here, you must know this formula. So the definition of resistance is just purely V over I. Okay, but in my in my secondary school, that's not how my teacher teach me. I'm always teaching you what my teacher teach me. So I'm not a teacher, it's my teacher is your teacher. Okay, so how my teacher teach me is they make V the subject. Okay, in a lot of textbook, they use this V is equal to IR. Not wrong, not wrong. Okay, if you rearrange, make V the subject, V equal IR is not wrong. Okay, but in my secondary school time, my teacher tell us how to remember. Okay, remember like this, like how Oscar remember V equal to Ri. Okay, how does my teacher teach me? In my time, I don't know about now. If it's the true, let me know. My time, Raffles Institution is one of the top school in Singapore. Okay, so so easy to remember RI, right? Because that's a top school in Singapore. Okay, so how the teacher teach me is, when you see this formula, V equal to RI, V is also another short form for victory. Okay, so my teacher teach us to remember this formula. Just remember, victory is RI. Is it lame? I can hear silence. Hey, because your mic are all off. Okay, so that's how I remember. Okay, that's how my teacher teach me, and that's how I teach you. Okay. Okay, so either of these three formula is fine. Okay, it's fine. In textbook, you will see the first and second one very often. Okay, the third one is how I remember. Okay, they are all okay. Okay, so which of these three formula you prefer? Okay, all of you type out the formula now. Which of these three formula of the resistor you prefer? Can you type it out and show it to me? Okay, Yuting, you like the second one. Why? Can you tell me why? The rest of you, can you tell me which of these three do you prefer? Okay, Oscar likes V equal RI. Beikwan also V equal RI. How Ray, why do you like V equal IR? Because that's the first formula that's introduced to you, right? Okay, so either of these three is fine. If you're taught that way, okay, usually the first one that you learned will be the one that you remember forever. Okay, I was taught V equal RI, that's how I remember to now. Okay. Can you think, does the teacher teach you any special way to remember? You were taught this one, but did the teacher teach you any special way? Like what? Victory equal to infrared. Yeah, anyway, all three is fine. None is better than the other because they are all equal. Okay, so I'm not trying to influence you. Well, the first one is better or the third one is better. That's not the case. All three are equally good. Okay, but the more important thing is which one can help you remember better. Okay, keep that for life. Okay, so what is resistance? Okay, the definition is voltage over or potential difference over current. But what does that mean? What does that mean? What does voltage over current means? Any idea? Okay, so resistance is equal to voltage over current. And then we learned that voltage is energy over charge. Okay? Okay, don't write like that. Voltage is energy over charge. Current is charge over time. So is there any funny thing that we can come up from here? You end up with this energy times time over Q square. Okay, that doesn't make sense. Okay, so basically, resistance is how much, that in general term, resistance is how much, okay, how much opposition it gives to current flowing through. Okay, the higher the resistance, the more opposition it gives to the current flowing through. Then because there's higher resistance, end up there will be less current flowing through. Okay, I repeat myself again. The greater the resistance, the less current it will flow through. Is that clear? Okay, I repeat one more time. The greater the resistance, the less current it will flow through. Okay, so let's look at J. Point J. Describe an experiment to determine the resistance. Okay, so how do we determine the resistance of this bulb? you are only given a voltmeter and an ammeter. And you know that resistance is V over I. So how do you conduct an experiment to measure the resistance of this? You do not know the resistance, but you're given a voltmeter and you're given a ammeter. Ammeter is the machine that measures the current. So I'm sure from here it's quite easy to understand, right? Let me explain to you. Okay, voltmeter. Okay, we use voltmeter to measure PD. We use ammeter to measure current. So my question is how to conduct an experiment, okay, to determine the resistance of this bulb. Okay, you know that R is equal to V over I. So what you need to do is you find the PD across the bulb. You find the V. Then you use the ammeter to measure the current flowing through the bulb. Okay, the ammeter you put in series with the bulb. If there's 5 ampere of current going through here, okay, in the same series, 5 ampere of current will flow through the same bulb. Is that clear? Okay, so how to explain perfectly is, okay, put a voltmeter in parallel with the metallic conductor and then record down the value. Then place a ammeter in series with the metallic conductor and then record down the value. Then use your calculator, okay, and then calculate the resistance by this formula, V over I. Okay, so for J, are you clear? Okay, that's a very simple way. So you have a voltmeter and ammeter, you can always find the resistance of any component. Okay, now the next thing that you all need to know is the effective resistance of a number of resistors in series and in parallel. Okay, point number K. Let me ask you a question. Let me draw 2 circuits for you, okay, or 3 circuits. This is the first circuit. On the left, I'm going to draw this circuit. And then on the right, I'm going to draw this circuit. Okay, so the box, okay, the box that I draw refer to resistor. Okay, so a rectangular box is a resistor, in case you're not aware. Okay, I'm going to draw a red color box. Okay, so I'm going to draw a red color box over the 3 resistors. Okay, so I'm going to have this one box here, this one box here, and this one box here. Okay, so if I were to combine these 2 resistors as one red color thing, what is the resistance here higher than this one or lower? Okay, so let me repeat my question myself. This is circuit A, this is circuit B. In circuit A, I have only one resistor. But in circuit B, I add one more identical similar resistor in series. So now I want all of you to type in the chat, which one has a greater resistance, A or B? Okay, all of you type it out now. Which one has a greater resistance, A or B? Okay, well done, Ryan. Yu Ting, well done. How about the rest of you? Okay, Hao Rui, well done. Yu Fen, well done. Oscar, incorrect. Okay, so let me explain to you. I want all of you to imagine that you are the current. Okay, you need to run in a circuit, circle and circle. Clear? So resistance is like a obstacle to you. Obstacle. And the obstacle has a, okay, for example, you're going to run through a field. Okay, this is door 1. Okay, there's door for you to run through. The second door only has a small hole to let you go through. So the first one, there's no hole. Okay, so for you to run through the hole, which one is easier? The one with no hole or the one with a small hole? Okay, so obviously the one with a small hole is harder to fit in, right? But you can still go through, but it takes more effort. Okay, so this one means it's a high resistance. Okay, so if you are a circuit, if you are a current, okay, if you are a current, you prefer to go through one obstacle or you prefer to go through the same obstacle 2 times. Okay, so to go through the 2 obstacles 2 times is harder for you as a current to go through. So therefore, B has a greater resistance. Does that make sense to you? Okay, so this is A, example A, this is example B. You know, this is not the correct example, sorry. Okay, basically, this is example A. This door thing is just a wire. If you go through the wire, there's no resistance, you can just go through easily. But if you meet a resistor, okay, if you meet one resistor, you got one hole there, you go through that, it takes effort. So 2 hole, okay, sorry, not 2 hole, 2 resistor means you must go through this door 2 times. So it's very hard. Is that clear? Now, my next question is, all of you are now convinced that 2 resistors in series is higher than 1 resistor. How about comparing A and C? If you are the current going through, which one is easier? Going through A is easier, going through C is easier, or there's no difference? Okay, tell me. A is easier to go through, C is easier to go through, or no difference? Yu Ting say no difference. How about the rest of you? Ray says C is easier. Then the rest, no. Oscar say no difference. How about the rest of you? Chelsea say A is easier. Okay, so I'm going to draw to you. All of you. Okay, let me use another thing to draw. Then I come back to this. Okay, all we can see this. So I'm comparing 1 resistor versus 2 resistors in parallel. Okay, so just now we mentioned let this be resistance be R. This is R. So the total resistance is just R, correct? Then for the first one, because it must go through 2 times, the total resistance is R plus R. Okay, I put 1 and 2, right? It will be R1 plus R2. Is that clear? The total resistance here is just add them together because you need to go through them 2 times. Okay, I'm going to give an analogy for the next one. So let's imagine you are the current at this point. You travel from left to right. Conventional current starting from left plus to minus, right? Okay, I'm going to have this point. Okay, if you are current here, you look in front, you see 1 resistor. If you are current here, you got two paths to go. Okay, you got two paths to go. You see two resistors in two paths. Clear? So for the first one, in front of you, this is what you see. In front of you, you see one door with one hole. Okay? So 7 of you have to go through that one hole. Clear so far? Now, for the one in parallel, you see two paths. In front of you, you see two doors. Okay, you got two roads. You have to choose. Okay, you see the same size of the hole in the door. But 7 of you go through one hole easier, or 7 of you half go to the left, half go to the right easier. Can all of you tell me now? Which one is easier? Okay, so if the 7 of you need to decide, the center one, all of you have to go through the same hole. But on the second one, on the right side, 3 of you can go to the left hole, and then the 4 of you can go to the second hole. Okay, and that's what exactly happened. If you have a current of 2 ampere, if the two resistors are the same, 1 ampere will go through the first one, the second ampere will go through the second one. Is that clear? Okay, so in this case, when you have two resistors in parallel, okay, okay, the total resistance actually drop. Do I make myself clear? The total resistance actually drop. And then there's a formula for this. The formula is like this. 1 over total resistance is equal to 1 over R1. This is R1, this is R2, plus 1 equal to R2. Okay, so this is the formula. And then when you realize we have a lot of 1 over something, this value will drop. Is that clear? Okay, so talking about resistance, you need to remember if the resistors are in series, you add them. When it's alone, it's just 1. But when they are in parallel, you also add them up, but they are all in inverse. Okay, so let me give an example. Okay, let me give an example. If this is 5 ohm, okay, this is 5 ohm, this is 5 ohm. The total resistance here is 10 ohm. The total resistance here is 5 ohm. Now, based on this formula, if I put the two 5 ohm here, can you calculate what is the, all of you can calculate what is the total resistance? Okay, based on this formula. Okay, all of you go and do that now. Sub in and then make RT the subject. Okay, do that now. I'm going to take my calculator as well. Okay, Howry, well done. Yiting, well done. So does that make sense to you all? So what's the total resistance for the one on the right? Okay, Howry, correct. Yiting, correct. Yiting and Chelsea, you need to write down the unit. Ryan, well done. How about the rest of you? Wei Kwan, are you there? Ethan, are you okay? Oscar, well done. Okay, so if you can give me the correct answer, means you know how to do the max. So I'm very happy. Where are the rest of you? Ethan, are you there? Yeah, Ethan, are you able to calculate? What will be the total resistance based on this formula? Pei Kuan, substitute. Okay, Pei Kuan, what I want you to do is, okay, I assume you are having difficulty. Okay, Pei Kuan, what I want you to do is substitute R1 with 5. Substitute R2 with 5. After you add together, you make RT the subject. And what is your answer? What's your answer? Okay, Yifan, well done. But remember to put down the unit. 2/5 is not correct. You need to inverse it. Okay, 1/RT is 2/5, correct. But what is RT? Okay, Pei Kuan, try again. Or you need me to show you the formula? Okay, write down here. 1/RT is 1/5 plus 1/5, correct? And then you get 2/5 is 1/RT. Then I want to make RT the subject. I need to inverse this. I will get 2.5 ohm. Okay, Pei Kuan, are you okay with the max here? Okay, so can you see? Conclusion here is, if you put the resistor in series, it becomes bigger. On the other hand, when you put the resistor in parallel, it becomes smaller. And I explained to you using the door. Is it helpful? I use the obstacle to show you, is it helpful to you when I use obstacle to explain? Give me some reaction, yes or no? Howry, are you there? You think, are you okay? All right. So this is the resistance in series and parallel. Okay. So we are done. We are done with H. We are done with I. We are done with J. So effective resistance we have done. Okay. Okay. L. Okay. Actually, all wire has resistance. But for simple calculation, we always assume that a wire has no resistance. So for this type of question, we are referring to resistant wire that has resistance. Clear so far? So for this part, we are referring to wire that has resistance. So what is the relationship between resistance and the length? So I give you an example. 1 meter, 2 meter. Okay, this is a wire, this is a resistant wire. Which one will have more resistance? The 1 meter wire or the 2 meter wire? All of you type it out now. Which one has more resistance? The 1 meter wire or the 2 meter wire? They are the same wire. You have to go through the obstacle for 1 meter, or you go through obstacle for 2 meters. Which one is more difficult? Okay, Ryan, understand? Okay, so therefore, the relationship you can say is the resistance is proportional to the length. Does it make sense? The longer the length, the greater the resistance. Okay or not? Make sense? Okay, now I give another example. Both is 1 meter. Okay, but this one, the diameter is 1 cm, whereas this one, the diameter is, don't want to be so extreme. The diameter for this one is 2 cm. So which one has a greater resistance? The 1 cm fat wire or the 2 cm fat wire? Which one has more resistance? The 1 cm fat wire or the 2 cm fat wire? So all of you type it out now. Yu Ting say 1 cm fat wire is more resistance. How about the rest of you? Oscar say 1 cm more resistant. Why? I thought wire fat would be more resistant. Why all of you say 1? Okay, Ryan say fat 1 cm. Okay, I think all of you get the same idea. If you were to look at the cross section of the wire, okay, what will you see? Okay, let me show you. Let me erase this first. Okay, so for the first one, all of you must go through this 1 cm. Okay, but for this example, the electron, okay, remember I told you electron flow is the electron that goes through. So if a wire is 1 cm of diameter, is it easier to go through, or if a wire that is fatter, which one easier to go through? Okay, so for the bigger area, it's easier for the electron to go through. So therefore, this one, the resistance is lower, and this one, the resistance is higher. Is that clear? Okay, so the bigger the area of the wire, the lower the resistance. So what is the relationship? Resistance is equal to K over A. Correct? The resistance is inversely proportional to the cross-sectional area of a wire. Understand so far? Any question for me? Now we combine these two formula together. Okay, you all can remember, the longer the wire, the more resistance, right? The greater the area, the greater the resistance, right? So when we combine this together, can we say that R is equal to K times the length over A? Are you all convinced about this? R is equal to K times length over A. Can you remember that? So K is a constant. There's a name for this. Every wire have a certain K. Okay? And this K is a constant. It's a constant for every material. So copper has a certain K value. Okay, gold has a certain K value. And then we don't use the word K. We replace the K with something else. Okay? And we replace the K with this thing called like rho, like density, like that. Okay, this thing, we call it resistivity. Okay, today my spelling is horrible. Okay, resistivity. Okay, let me just rewrite. Resistivity. Okay, so every material have a certain resistivity. Okay, resistivity. Here, so gold may be higher. Okay, copper may be lower. Okay, you can actually Google what is the resistivity of certain material. Okay, so some material have higher resistivity, some wire has low resistivity. But this resistivity is a constant for the same material. Okay, something like density. This formula, this picture is like density, right? It's like a rho, correct? So it's the same as every material has a fixed density. Likewise, every material, every metals has a fixed resistivity. Clear? And the resistance go up if the length is longer, and the resistance goes down when the area is longer. Clear so far? Are you all okay? If you understand perfectly, give me a clap reaction. Okay, if you understand perfectly, give me a clap reaction. Okay, all the clap disappear already. Okay, let me continue. Okay, let me talk about the unit. Okay, let me talk about the unit. The unit for resistance is ohm. The SI unit for length is meter. The SI unit for area is meter square. So can you tell me, can all of you go and calculate what is the unit for resistivity? Can all of you calculate what is the unit for resistivity? Okay, all of you do that now. Okay, Howrey, you're correct. Well done. How about the rest of you? What is the unit for resistivity? Only Howrey got it correct. Maybe I should write somewhere that's look nicer. Resistance is resistivity times length over area. So resistivity is area times resistance times area over length. So what's the unit for this? Xiao Xing, well done. How about the rest of you? Okay, Oscar, well done. Yu Ting, well done. How about the rest of you? Okay, Oscar, well done. Yu Ting, well done. Howrey and Chelsea, well done. How about the rest? There's 3 more of you. Okay, so are you all convinced that the unit for resistivity is ohm meter? Okay, I don't need you all to memorize this. I'm just giving you all practice how to find the unit for this. Okay, next. Next, we are done with this. Okay, so we have talked about R is equal to V over I, correct? And this is only true, okay, if your component obey the Ohm's law. Understand? Okay, so this formula is only true if your material obeys the Ohm's law. So what is Ohm's law? Okay, so you look at this. Ohm's law means that the current flowing through the component is directly proportional to the voltage across it. So Ohm's law is when, if I were to draw Okay, if I were to sketch, okay, if I were to sketch I versus V graph, okay, the graph should be straight. Okay, it means that if I were to increase the current and the voltage proportionally, the gradient will remain the same. Clear so far? Can you see over here? This gradient is actually I over V, which is actually 1 over R. Understand? Okay, this gradient is I over V, right? I over V is here, which is actually 1 over R. So whether is it 1 over R, R over 1, the resistance is the same. So increase the current, your resistance remain the same. You reduce the current, your resistance is still the same. So most component actually has a fixed resistance. So regardless of how high your current is, your resistance is the same. Okay, so Ohm's law says that a current passing through the metallic conductor is directly proportional to the potential difference. Understand so far? So this is Ohm's law. Ohm's law means I is proportional to the V. In other words, I is equal to kV. And this K is your 1 over R. Understand? So if I is proportional to V, your constant is the same, and your constant is your R or 1 over R, and you get a straight line graph. So this is Ohm's law. Clear? Okay, but this way I explain is quite hard to understand, right? I repeat one more time. I is proportional to V, which is also the same as V is proportional to I. So V is equal to Ki. Okay, V is equal to Ki. This is your proportional that you learn, proportionality you learn in Sec 2 max, right? And this K happen to be your resistance and it's a constant. Okay, so Ohm's law states that current and potential difference are directly proportional. Okay, so the constant R is your resistance. So the resistance is constant. Clear so far? Okay, so we have done with Ohm's law. So Ohm's law is very similar to I. Basically, Ohm's law is just describing I. Okay, where I and V are directly proportional, and therefore you have a resistance. And resistance is constant. But not all material will give you a constant R. Okay, so this formula is not wrong. To calculate the resistance, okay, you need to measure the V and the I, it can give you the resistance. But Ohm's law says that V and I are directly proportional. Okay, so what Ohm's law is trying to say, suggest is that if V and I are directly proportional, your resistance remains the same. It remains a constant. So therefore, all ohmic component, any conductor that obeys Ohm's law, okay, will have this kind of characteristic. If you draw an IV graph or a VI graph, you get a straight line. Okay, so any ohmic conductors will give you a straight line graph. It means that I and V are directly proportional. You get a straight line passing through 0, and this is the and this is the what it means by ohmic. Okay, where the resistance is constant. Am I saying too many things today that you may get blur? Can? Okay, so I've gone through a metallic conductor at a constant temperature. You get this type of graph. Clear so far? You get this type of graph. Understand? Okay, I'm going to finish up soon now for today. So we are done. I've gone through summary of all this. Okay, so what happens when temperature increase? Okay, when you increase your temperature. So earlier on we talked about the length and the cross-sectional area. Okay, we know that when the length increase, the resistance increase. When the area increase, the resistance decrease. So now what happens when temperature increase? Okay, some of the metal, the resistance will go up. Some of the metal, the resistance will go down. Okay, so it's not fixed. But generally, when temperature goes up, the resistance will go up. Yes, so far? Generally lah. Okay, why? Okay, why? Because when temperature goes up, the particles move faster. Okay, move faster. So it will be harder for the electron to flow through. Am I right to say that? And when the temperature goes up, the subatomic particles actually move faster. There will be more obstacles. So for example, for you to run through a crowded place when they're all not moving or they're moving slowly, is it easier to run through? Or is it easier to run through a crowd when they're all running very fast in random direction? Can you imagine that? So if they are running very fast, that's when temperature goes up. You're more likely hit another person. So therefore the resistance goes up. Clear? Does it make sense? Okay, let me go through the last one. So we are supposed to draw the IV graph of three things. 1, metallic conductor. 2, the filament lamp. 3, a diode. Okay, number 1, IV. So when I talk about IV characteristic, the first letter is the y-axis. Okay, second letter is the x-axis. Clear? Just like in your SPA, when you need to draw a IV graph, the first letter is your y-axis, the second letter is your x-axis. Okay, so for number 1, this is an ohmic conductor. Okay, as I mentioned to you, number 1, this is how it looks like. But at the same temperature, when you increase the current, your potential difference will go up proportionally. Okay, filament lamp. Okay, filament lamp, how does it look like? Okay, this one I'm not totally sure, but it looks like this. Okay, so as the current go up, okay, as the current goes up, the voltage itself or the potential difference itself, hold on, goes up even more. Clear? Can you see? When it is here, the potential difference is here. When I double it, the potential difference is higher. So as the current goes up, the potential difference goes up even more. Okay? Okay, and lastly, a diode. Okay, I think you haven't learned this before. This is a diagram of a diode. Okay, in a car, okay, what does a diode mean? Let me have this battery. Okay, never mind. Okay, a diode only allows the current to go through in one direction. Okay, for you, that's the, I want you to just remember this for now. A diode only allows the current to flow in this direction. So in this case, current can only flow in this way. This way, it will not flow. Can? So if I were to draw an IV graph, in one direction, there will be current. In the other direction, there will be almost no current. Clear? Okay, so a graph of a diode should be something like this. On one direction, there is current. The other direction will be zero. The current will be almost like zero. Is that clear? I will show you more example of this next week. So basically, a diode allows the current to flow in one direction, but not the other. Clear? So any question for me? Okay, so I got two acid question for you all. Okay. In fact, I got a lot of acid question. So I want you all to tell me, number one, how much did I value add to you for today? So you describe. Okay, number two, give me the formula for current, PD, and resistance. Okay, once I call your name, you may go. So for the first question, you may just tell me, I learned nothing from me, or you learn certain things from me, or you find certain things very useful. Okay, just tell me what you think from today's lesson. Just give me like one sentence feedback. Okay, number two, tell me the three formula. Once I call your name, you may leave. Okay, thank you so much, everyone. Okay, thank you, Chelsea. And give me the formula. So Chelsea is a good revision for you lah. You did not learn anything extra, but it's a good revision lah. That's what you mean, right? Okay, Chelsea, that is the formula for R. How about formula for V and I? What's your formula for V and I? Okay, I'm going to end the recording. Then you all continue to write down what you have learned today, and then I'll call your name once I read. Thank you.